Good morning, everyone. I want to welcome you to another Motivate Statistics class. Of course, today the focus is going to be on correlation matrix. On Monday, I remember I walk you through covariance matrix. Let me tell you this. The significance of covariance and correlation matrix in statistical analysis cannot be overemphasized. So this actually play a huge role. Okay, if you're trying to understand your data structure, particularly situation where you got a lot of variables, and of course your interest is to investigate how these variables move, whether they move together or they move apart. That is, you want to be able to understand the relationship among variables. You want to figure out the dependency of these variables. Of course, we normally use covariance or correlation matrix. But let me tell you this. Um, the difference between correlation and covariance matrix, the two of them, of course, they actually, you can use them to investigate relationship among variables, except that why covariance only handle the direction of the relationship. Okay, covariance does not handle the magnitude or the strength of the relationship. Okay, but when you talk about correlation, or on the other hand, correlation handle both. Correlation handles both the direction and the strength of the relationship. You know what do I mean by the direction? I mean, is it positive? Is it negative? Or even zero? Zero means no correlation at all. And what do I mean by the strength? What I mean by the strength is it weak, even if relationship exists? Is it weak or strong or moderate? That's exactly what I mean. And let me also say this. Uh, Correlation normalizes covariance. And that is the reason why do we need the normalization? Why do we need to standardize covariance for us to be able to get correlation? Is because we will actually want to reduce the influence. There could be some variables. If, for instance, if you are working with different variables, they actually going to have, they could have different scales and different units. Okay, so using covariance, for that kind of situation where variables have different units or they have different scales, there's possibility you're actually going to see some variables could dominate the others, and that could impact result. And that is the reason why we need correlation. The correlation is to standardize that, is to remove that influence in such a way that it's actually going to bring all the variables into the same scale. Does that make sense? Okay, so I want to, like I said, this is what I have for the week. I've walked you through the data matrix and covariance matrix on Monday. Of course, the focus today, like I said, is the correlation matrix. But before going into, because what I'm going to be showing you is a mathematical, maybe theoretical foundation of days, you're going to see something that has to do with algebra. But before I start showing you the algebraic provisions, okay, for correlation matrix, I think it becomes necessary for you to understand, you know, the significance of correlation matrix in statistical analysis or in multivariate analysis. So what is the significance of correlation matrix? Number one significance, in principal component analysis, where we believe variables are correlated, okay? Variables are correlated, okay? Now, the idea of a correlation matrix can be used to convert the correlated variables into uncorrelated principal components. Does that make sense? Variables that are correlated, okay, they are correlated, okay, so how can I actually generate uncorrelated set of variables? The idea of a correlation matrix can be used in that regard. Another significance of correlation matrix, if you work on multiple linear regression, particularly you're focusing on multivariate regression. Let me be specific. You actually fitting multiple linear regression. Okay, maybe I'm looking, the X1, the X2 up to the XP, they are the explanatory variables. So I may actually want to look at the effects of these variables on Y, okay? And of course, this regression has parameters, beta naught, beta 1, up to beta P. And of course, this guy is the error time, okay? When we specify statistical model, we normally have a deterministic component, okay? We normally have a deterministic component, okay? We normally have a deterministic component and random component, okay? Now, if my intention is to explain, if my intention is to isolate the effect of X1, X2 up to XP, for instance, I'm actually going to be specific now. If this guy is wage, okay, if this guy is wage, okay, if X1 is numbers of years of education, okay, and this guy is actually the numbers of years of experience, numbers of years of experience, okay. We have so many other variables that maybe one of the variable may be gender. Another variable may be the kind of or department you find yourself in that company, whether you are in clerical or so like that. Okay, now this is a model that we can actually use to explain weight. So if I want to look at the effects, okay, if I want to look at the effect of numbers of years or numbers of years of education, okay, of the worker on the wage, I also want to look at the effects of each of that, then we have assumptions, okay. Every statistical model has assumption, and if you take a look at the error, assumption in statistical model relies on the error, okay. Now we have assumption. One of the assumptions, okay, one of the assumption is that error should follow normal distribution with a mean of 0 and the constant variance. There's so many assumptions, but there's one particular one that is connected to correlation matrix that I'm going to talk about. It is the assumptions of absence of multicollinearity. Absence of multicollinearity. Okay, that assumption is that the explanatory variables x1, x2 up to xp must not correlate. If they do, there's going to be a problem with this model. Does that make sense? Now, when variables are correlated, okay, how am I going to know if variables are correlated, the correlation matrix will enable me to know if variables are correlated. Don't forget, the correlation matrix will give us a pairwise correlation between any of these two, between two, and maybe between S1 and S2, S1 and S3, and so on like that. So I'm actually going to say in regression analysis, correlation help us to check whether the assumption of no multicollinearity hold. Does that make sense? That is one of the significance. Another significance of correlation matrix is very useful in machine learning, where we got so many variables, and because you want to avoid redundancy, okay, we can actually use it in dimensionality reduction. We got so many variables. Okay, the fact I got thousands of variables, it may not be all of them that are useful. Okay, the correlation matrix can actually help us to eliminate some irrelevant variables. Okay, and when you eliminate some irrelevant variables, of course, it's like you are filtering out the noise. Okay, the more you are able to filter out the noise, the better your model. Does that make sense? And that's exactly what I mean. Now, it's also useful in portfolio optimization in finance. Portfolio optimization in finance. Okay, portfolio optimization in finance. I got so many assets. Okay, situation where assets are correlated is dangerous. Because when I said if I have asset one, asset two, asset three, if they are correlated, it means if I lose in this asset, I'm likely going to lose in the other asset. So with the correlation matrix, we can actually construct an optimal portfolio, the optimal portfolio that can reduce risk. Okay, now you understand the reason why we do what we do. Okay, now we want to go into the math. We want to go into the math now. Now, take a look at this. This is a typical correlation matrix. Correlation matrix in the diagonal, it's actually going to be 1, 1, 1, 1. I want to award an extra credit. Can somebody tell me? Why is it 1, 1, 1? Not theoretically. I need a practical answer. Why is the diagonal of a correlation matrix 1, 1, 1, 1? Extra credit. Go ahead. Exactly. Exactly. Send me a message for extra credit. You have 1 point. So if I'm looking at the correlation between numbers of years of education and numbers of years of education, I expect a perfect correlation. Does that make sense? Because it's the same variable. Okay, that's why the diagonal, the half diagonal, okay, the half diagonal, it could be greater than 0, it could be less than 0, the half diagonal could even be 0. That's no problem. Does that make sense? But the half diagonal, okay, in theory, in practice, it can be 1. We can never have a perfect correlation between two different variables. It's not going to happen. Does that make sense? Okay, now what we're trying to show you right now is just to show you what is behind the scene. Okay, in case you are working with software and you're working on correlation matrix, what they actually program, the formula, I told you the other time, the formula, computer is not going to work. Software is not going to work without human brain. I say that all the time. Okay, some people have argued this out, whether the AI will replace human knowledge. It is capitally no, it's not going to, because AI can't do anything without human being behind. There's a lot going on behind the scene. Now, what we program behind the scene is what I just want to show you now. Okay, mathematically speaking, if I want to compute correlation, okay, on for each, if you look at that correlation matrix, how do we compute the entries? Okay, now we're going to go by way of formula. This is what I'm trying. So if you take a look at this particular guy here, Okay, it's trying to tell me correlation between any two set of variable is actually the ratio of the covariance to the product of the standard deviation of each variable. The SJK is the covariation. The Sj and the Sk, the Sj is the standard deviation for variable Sj, and Sk is the standard deviation for variable Sk. Okay, and the formula now is what you are seeing here. Of course, I believe you're not seeing this for the first time. In a lower level statistics, you've seen this formula so many times. But we're just trying to refresh your memory on this formula so that you'll be able to know what is programmed behind the scene. Now, that is the final formula, the final form of the correlation formula. But let me tell you this. Because I'm actually going to be working with data heads. You remember on Monday, I show you a data matrix. If the whole thing is going to start from data matrix, and from the data matrix, how do we manually, or how do we show algebraically, or how do we show mathematically how do we derive correlation from a data matrix X? Now, from a data matrix X, I need you to pay attention. That is what we use. Okay, what is the SS? You remember the SS? Oh my God, what am I doing here? This data matrix, I've already standardized the data matrix. This is not the way it was initially. Okay, what do you think I did to the data matrix? I subtract the mean of the variable in that column and I divide by standard deviation. Whenever I'm doing that in statistics, I'm standardizing. Does that make sense? Now, after standardizing that, I'm actually going to have a matrix XS. I'll find the transpose of that. I will multiply. So if you take a look at what I'm doing here, I'm actually multiplying the transpose of this guy by this guy divided by n, and that's going to give me my correlation matrix. Okay, that's going to give me my correlation matrix. So why do I care to know? Since I can use my software, things are changing. With reality is dynamic. Reality is not static. If you understand the formula program behind the scene, you can adjust because the formula that we have may not be realistic anymore because things are changing. And that is why you need to be able to understand what is programmed in the software. Okay, now that is a correlation for you. And the assumption is that, since if you take a look at the denominator here, you're actually going to see that each of that is standard deviation. And there's no way I will be able to get standard deviation without four of us getting the variance, right? The variance is the one with a square. And when I find the square root of of variance, I get the standard deviation. Then the assumption is that that variance has to be positive. This guy here has to be positive. Okay, it has to be non-negative and it can be zero. Okay, if it is zero, what happened mathematically? Okay, if it is zero, okay, what happened mathematically? Your correlation will be undefined. Don't forget, you got a standard deviation in the denominator of a fraction. When the denominator of a fraction is zero, it's undefined. Okay, and that is the reason why we are actually placing a restriction on that. Okay, that's why we're actually placing a restriction on that. Okay, now give me 1 second. I think I just want to check something. Okay. I'm just trying to confirm my seminar presentation today. Time. Oh, 11:10. 11:10. Okay, so today is the day of my seminar. Is gonna the time is 11:10, Ford or 150. Okay, Ford or 150. I'm just confirming that. Okay, now back to business. Okay, the variance have to be positive. Okay, for that to happen. And of course, you know, uh, if I the situation under which correlation is going to be equal to one is when you are talking about the same variable, just like what the gentleman said the other time. Okay, now we know then the trace of R have to be that in such a way the sum of the lambda has to be that. So the sum of the variance that we talk about. And of course, I actually also impose this condition on Monday when lambda j is equal to 0. Okay, that only happen if n is less than p. When the number of observation is not less than the numbers of features. Okay, and of course, if sj is greater than 0, then we have s linearly independent, because what we actually targeting is linearly independent. Okay, and then the formula of correlation makes sense with the Cauchy-Squarce inequality. Okay, if you take a look at this, if I square according to Cauchy-Squarce inequality, if I square covariance, if I compute a covariance from two variables and I square it, okay, if I want to compare that to the product of the variance of each by Cauchy-Squarce inequality. Okay, the square of covariance is less or equal to the product of the respective variance. Okay, and if I perform algebraic computation like dividing both sides, if you take a look at this, dividing both sides by the product of the square of the variances, I'm actually going to have this, right? I'm actually going to have that. And if you take a look at that, oh my God, if you take a look at that, you remember the other time I said the correlation JK is SJK divided by this. And from Scotchy, okay, what that means is I'm squaring this. You see that by Scotchy? It means I'm squaring that. That is by Cauchy, and that implies the other side is a square of the correlation. So which means the square of the correlation is going to be less or equal to 1. Of course, we all know. Can somebody remind me in statistical analysis, there's a particular name that we call the square of the correlation. What is it called? Extra credit. There's a correlation, right? Okay, we also have the square of the correlation. It's called a name. What is that? Yeah, it's R square, but it has a name. Or what is the difference between correlation and R square? So I can give you that extra credit. For regression model, what does it do in regression model? You're very close. Exactly. Send me a message for extra credit. Now let me tell you this. Correlation, we measure the strength and the direction of the relationship between variables. But when I square correlation, it is no longer called correlation. It is called coefficient of determination. It is called coefficient of determination. Okay, what is the function of coefficient of determination? I want to come back to this example, just like what he said. He said in regression model, I want to tell you something now. Okay, now we are seeking the explanation. We believe that in wage, there is 100% variation here. There is 100% variation in wage. And we actually want to quantify the amount of this variation that will be explained by the variables x1, x2 up to xp. And let me tell you this. This is the module. I told you deterministic component is the module aspect. The module cannot explain 100% variation. The best module, the best module, can you hear me, right? Okay. The best module cannot explain 100% variation. Okay. Now, because of this guy. So the explanation from here, here we call it module explanation, like explain variation. Then here, unexplained variation. There's always going to be unexplained variation. So R squared, the coefficient of determination, R squared, the coefficient of determination, okay, measures how much percentage variation in the response the model can explain. Does that make sense? R squared measures how much percentage variation in the response the model can explain. And that is why here you say less or equal to 1. Okay, less or equal to 1. Okay, realistically, it can be 1. This is just in theory. Okay, because the model cannot give exact characterization of reality. Model is not the same as reality. Because of that, we do not expect R squared to be 1. Okay, it's going to be less than 1. Okay, and we multiply by 100. Okay, let's say we got 0.8, then 80%. 80% means, what that means is the model, okay, the model that is the numbers of years of education, the numbers of years of experience, and some other factors explain 80 something percent variation in wage. Then the remaining one is unexplained, which is what we're going to have here. But what are we trying to do in a model? We want to try and minimize the unexplained. We want to minimize the unexplained. But the best model, okay, no matter how we do, okay, this guy can never be 0. No matter what we do, it can never be 0. Does that make sense? Okay, so as for that, I'm actually going to move. Now, I promise I'm actually going to show you the computation in R. Okay, because we use software for this course, of course, you need to be able to know how to do that. But let me tell you this. We got hard way to do that in now. We also got easy way. So I'm showing you the hard way. Like for instance, I have data set, and my intention is to figure out correlation matrix, okay, from the data set using R. I want to use our software. Okay, this is the hard way to do it, because here I'm just coding a lot. Okay, I'm directly coding the formula. Directly coding the formula. Okay, so this is serious. Okay, this is still going to give us what we want. Okay, I'm still using the same data as Monday. Okay, but what is the easy way? Okay, we want to save time, right? What is the easy way? This is the easy way. Oh my God. I remember on Monday, if you want to find the covariance matrix, and now you're gonna write co, right? But we're gonna write COV, but for that is for covariance, but for correlation, it's actually gonna be COR. Take a look at that. It's actually gonna be COR. You see that? You define your matrix X. If you do COR, because you're actually gonna get, you can get the dimension of your matrix here now, DIM of R, 11 by 11. Okay, and of course, if you if for instance you want to focus, you actually want to, maybe you are not interested in the entire correlation matrix, you are only interested in just 2 variables. Okay, that is what this guy is trying to talk about. Do you know, with this we just R, okay, into 1 and 2, that will give me the correlation between x1 and x2. Another way to do that, I'm also going to get the same results. I can go by this. I can do core, okay, specify the matrix S, then I do the one in column one, maybe this guy, MPG and CYA, they occupy column one and column two in your data frame. That's another way to do that. So it's going to give you the same result. Another way to do it if I want to waste my time, because I'm seeing the third way, wasting my time, programming, I'm programming the formula directly. You see that? The programming the formula covariance of this divided by the standard deviation of that, the standard deviation of that. I'm wasting my time. That's still going to get the same result with others. Okay. And of course, if I may be interested in a subset of the entire data frame, maybe I want to if you take a look at this guy now, okay, row 1 to 3, you see that one, and 1 to 6, you see that one, okay, and you're actually going to have the corresponding correlation value. Now, what have we done today? I've actually walked you through, okay, how to compute correlation using both the hard way and the easy way. I will advise you to go for the easy way to save time. And I've also given reason, why computing correlation matrix is significant in both statistical world and machine learning world. Ranges from dimensionality reduction, to, risks or, portfolio optimization in finance, to solving or checking for problem of multicollinearity in linear regression, and also, go all the way in principal component analysis where you want to convert correlated features into a uncorrelated one. The correlation matrix can actually be used. Even in factor analysis, where some variables are actually correlating. And why are they correlating? Okay, I actually want to identify some hidden factors that could explain that relationship. That's what we call factor analysis. Of course, I'm going to use the idea. I'm going to start with the correlation and matrix if moving forward. Okay, and I also show you the formula, mathematical formula, what was programmed, behind the scene. And what is next? What is next is to walk you through some miscellaneous topics in this area, and of course, that will be done. So, which means if you want to watch out for the assignment that is coming, the next assignment, you're actually going to center on this. Of course, I provided a code. So what I would advise is to you adjust the code, to suit whatever data set you give me. Does that make sense? Okay, I'm stopping early today. Yep. That makes sense. Any question? Is there any question? Okay. Be sure you all stay safe. Have a lovely day. You are invited to my talk. Bye for now, everyone.